Hi everybody, it's January 2024. I wish everyone a happy new year and I'm back with new videos from the world of Godot shaders. And I'm also planning to record something about modeling in Blender. Anyways, the first video of this year is dedicated to a shader that can be used for interesting post-processing effects and uses the Sobel operator along with other algorithms such as the Gaussian blur. Let's dive into it. So, what kind of effect are we going to create? First, I would showcase the result. This is my third-person controller project. Let's just display it. You might remember that it's with snow particles and the shield and the third-person controller, so that could be enough. And now I will activate the canvas layer with the shader. Let's run it again. Okay, this is the result. As you can see, the shader detects and highlights the edges of objects, while the rest recedes into the background. This edge detection is implemented using the Sobel operator, which I mentioned at the beginning of the video, and it's often used for digital image processing. I won't bore you with a detailed explanation of the algorithm. For the purposes of the tutorial, it's enough to know that the Sobel operator is applied to each pixel using a so-called kernel, which is a 3x3 matrix containing the given pixel and all its neighboring pixels. Let's take a look at the Wikipedia definition, which will shortly translate into the Godot shading language. Very briefly, we are working in 2 dimensions. So we'll perform signal processing on each pixel using a convolution operation with a kernel matrix in the x and y directions. We'll then use both results in the final formula, here it is, to obtain the so-called gradient magnitude, which will correspond to the resulting color of the pixel. If you don't fully understand it, don't worry. I'll clarify everything once again as we write the shader code. So let's switch back to Godot and we'll start with the usual shader type, render mode and the screen texture. So first I will create a new shader in the shaders folder. So it would be resource and shader, canvas item, and let's call it Sobel. Okay, create. And here it is. Let's use it in this color act, dragging to the shader property. Okay, and as I said, let's just double click to open it in the editor and move it a bit further. And the canvas item, we should use a render mode and shade it because we don't expect any form of shading in this effect and it should save some GPU power. And we won't need the vertex function. Let's get rid of it and let's delete the light function as well. And as usual, we need to import the screen texture, and since we are working in Godot 4, it is not declared by default like in Godot 3. Let's do it right this way. Uniform sampler 2D screen texture, and it is hint screen texture. Yes. Repeat disable filter nearest. I think I explained these options in my previous videos, so I guess it's unnecessary to do it again. Just let's say this is the best solution, the best combination for the full screen post-processing shader. Very well. So, as I mentioned, we'll be performing a convolution operation. So let's prepare the corresponding function. For now, we'll leave it empty. It would be vector 3. Let's call it convolution. and we will need the sample 2D texture, let's call it text, coordinates of the current pixel, UV, and we'll be working with a pixel size, which we'll take from the built-in screen pixel size variable size. Okay, and as I said, it would do nothing, so let's just prepare the vector we will calculate here. Let's call it conv, and it would be, the initial value would be just 0 vector and return conv. Alright, now let's implement the fragment function. We'll start by defining the 3x3 matrix for the Sobel kernel, and for simplicity we'll create it as an array of 9 elements. For clarity, I'll comment on which indices correspond to which matrix cell. Yeah, sorry, here, vec3 pixels, and I said it would be 3x3, so it has 9 elements, and let's just clarify the order if it's translated to a matrix. And 6, 7, 8. Very well. Now let's use the convolution function. We'll iterate over all rows and columns of this matrix and save the result for the given pixel and all its neighbors. Let's create the cycle for int row from 0 to less than 3, so it would be just 0 to 0, 1, 2, and row plus plus. And for columns the same. Call from 0, call less than 3, call plus plus plus. All right. And now we need to take the coordinates of the current pixel, and since we're working with the matrix, we will shift the coordinates by the current column and row. Let's do it. Vec2 UV is screen UV because we are working with the full screen, and the shift, so vec2, and now we need to convert the integer to float, so it would be float and call -1, because the column goes from 0 to 2, but we need values like -1, 0, and 1. That's why we are subtracting 1 from this, and the same for the row, float row -1, and we need to multiply the result with the dimensions of the actual pixel size on the screen to get the consistent effect regardless of the screen pixel size. And as I said, we need to apply the convolution function and save it to the pixels array. Let's do it. Pixels, and now we need to calculate the index in the array by the column and row of this matrix, so it would be row by 3 plus column, and it's the result of the convolution function, which takes our screen texture as the parameter, second parameter is UV, and the third one again is the screen pixel size. Very well, so the matrix is filled with values, and we can apply the Sobel operator to calculate gx and gy, as you remember from the Wikipedia page, hopefully. If not, you can always look it up, and I will explain the algorithm right away. Okay, let's apply the Sobel operator. So I'll just mark it here, like Sobel operator. And as I said, we start with gx, which is vector 3, and the calculation would be something like this. Let's just put it to multiple lines so the code is better readable. And the convolution operation, I mean the matrix operation, would be this one, pixels 0 multiplied by -1 plus pixels 3 multiplied by -2. These are the coefficients from the Sobel operator as it was defined on the Wikipedia page. And finally, pixels 6 multiplied by -1. So as you can see, 0, 3, 6 is just like this column, 0, 3, 6. That's why I just written these comments here to make it more understandable. And this is just the first part, and the second one plus pixels 2. Now we are working with the final column multiplied by 1 plus pixels 5 multiplied by 2 plus pixels 8, yeah, multiplied by 1. Okay, not here, right, this is correct. Very well, and we will do the same for gy. I'll just copy and paste to make it faster. So gy would be, and now we are working with rows, so pixel 0, 1 and 2, and the third row would be 6, 7 and 8, and we need to fix the coefficients as well, or maybe not. No, they will be the same. Great. And finally, let's make the square root of the sum of the squares, as we saw on the Wikipedia page, this line. Let's get back and calculate. Back 3, let's call it Sobel, as it is the final result. Sobel. And square root gx to the power of 2, so gx by gx, plus gy by gy. Very well. And we can assign the final value to the color. Like 4, Sobel for the first 3 elements, and the final one is alpha 1. Okay. Now when we run the project, let's do it, we'll see that nothing is displayed. This is because we haven't implemented the convolution function yet, and it currently returns a 0 vector each time. Let's fix that. We will use the same algorithm as for calculating the Sobel kernel, but this time we will add the results to an accumulator, which is this vector3conv. This is the basis of the convolution function. So let's do it. For int row, let me just copy and paste to save time. Okay. Here it goes, and let's fix the curly brackets 1 and 2, and now we're adding to the accumulator, so conv plus equals, and now we need the pixels from this from the texture, from the screen texture, so we'll use the function texture for the texture text and coordinates UV, and again we are working with the neighbors, so we will use the vector 2 and again casting to float, call -1, the second one would be float row -1, okay, and of course we need to multiply that by the pixel size. And finally, this is the 4-dimensional vector and contains alpha as well, so we'll just take the RGB part of it. That should be fine. Let's run the project again. Okay, we can see some result. It's not the worst, but it seems that the highlighting of all the contrasts is a bit too strong. We'll achieve a better result by incorporating some blur algorithm into the convolution function. Let's try, let's close it, and let's try Gaussian blur. But before we do that, I'll briefly describe what it involves. Once again, let's turn to Wikipedia, where on the relevant page we can see that Gaussian blur uses the following formula. Of course, we won't perform such real-time calculations because we only need to compute the coefficients of the so-called Gaussian matrix, which is here is a sample, and which we will then use to adjust the convolution function. But how we can do that? Let's switch to this page. There is a very nice article about calculating the Gaussian matrix, and this is the example of the 5 by 5 matrix, which is exactly what we will use. I won't manually type the entire matrix. This time I'll use copy and paste. So let's get back to Godot, and let's do that. So we need to insert the matrix here, and I'll open my prepared document, copy and paste. So this is the Gaussian matrix, and what needs to be done, we need to increase the number of rows and columns from 3 to 5 and multiply the result by the coefficient from the Gaussian matrix. So it would be multiplied by Gauss, and again we need to calculate the position in this array related to the matrix cell. So it would be row by 5 plus col. Is that all? Yeah, so let's try to execute the project again, and we should see a much better result. Yeah, we do. I think it is precisely what I've been showcasing at the beginning of this video. So it's much better, wouldn't you agree? It may not stand out as much in this scene because it contains few objects and the background is too dark, if we just ignore the snowflakes. But what if I tried applying the same effect to our point-and-click adventure game, which I presented in one of my previous videos? It should be quite easy. We'll copy our code and open the game project. So Ctrl A, Ctrl C, project, and quit to project list. Let's select Whispers of Prague and wait for it. Okay, here it goes. This is the main scene, and we already have a canvas layer here, so I can simply add another color act. And here it is. And in the layout, let's use the anchor preset full rec to cover the full screen. And we need a material, shader material as usual. And click new shader. I'll just keep the name main because I will delete it anyway, and create, click, and paste our shader. Okay, and here it goes. Let's start the game and see how it looks. Okay, it's not bad, it's completely different. What if I start and show some scenes? It doesn't work. I cannot click. Do you know why? That's because the canvas layer just the canvas layer is on the top of everything else and it swallows the mouse events. Let's see how we can fix that. So I need to switch back and kill it right here. And we need to click the color act, find the mouse section, and in the property filter we need to set to ignore. Now when I start it again, it should work as expected. Yeah, now I can click new game. I think even the text is pretty readable. Yeah, this is something like surreal, I would say. Let's try some more scenes. Have a look at the Prague Castle. Very well, let's close it. And once again, exit the game. And that's all I have prepared on this topic. I hope you liked the effect, and there are certainly various ways to enhance it. For example, experimenting with different coefficients for the Gaussian matrix, using larger matrices than 5 by 5, converting the results to grayscale, etc. However, it's essential to be careful not to overdo it with post-processing. After all, we're working with the entire screen, and a large number of calculations could negatively impact the performance of our game. Anyway, I believe the Sobel operator and edge detection have a lot of applications. So have a great time and see you in the next video.